like, I don't know. I feel like I'm pretty even in all like categories. No, like when I get like, I'm just like not amazing at one thing.
Wow, it comes back to the bajillion comments.
But I will say like, it's like.
Everything.
What did we do Friday?
Huh?
What did we do Friday?
I don't know. I wasn't. Oh shit.
We have a quiz today? What?
Oh.
I wasn't here.
No, not me. I ain't doing that.
No, I wasn't here.
You trying to dip?
I'm leaving at 3.
Well, let's just go right now. Yeah, it was cold here. No, it wasn't here. Mr. Johnson, if we weren't here Friday, do we still have to take a quiz?
You should. Was it school business?
Yes.
Yeah.
Well, that's considered a planned absence. You knew you were going to be gone, right?
Yeah.
And so, what's the delay in getting caught up? I can let you do it during advisory on Wednesday, but in the future, when you miss for school business, you're supposed to be caught up before you come back.
What did we do Friday? I'll sign up for Wednesday.
We did a practice. Okay, so. So the range is the domain is when you plug in the points and you graph it. The inverse is the opposite. When you plug it in to do it. What is 0 squared minus 1?
The negative total.
It's negative 1. What is 1 squared minus 1? It's even this is the inverse, so you plug it into 2. But then it's just the opposite of this. So then it's going to be negative 1, 0. 0 and 1.
You want me to sign up for Wednesday, Mr. Johnson?
Yes, please.
I'm telling you, you graph that. You know what you're doing. You've done it. How far down and how far up. Okay. So, good. And you graph it. Once you graph it, you just know. The first one's top one, then it goes to the top one. That's the opposite of the range. Inverse function domain is the same.
For the full kind of context, I do should turn my hand.
Yeah. Yeah.
And he missed Friday.
We did that. What is that?
Lisa, she won't be here. Cole, she dismissed that. All right, if y'all did not turn in 87 into Google Classroom, make sure your name's on it and come give me your hard copy. And I also need your phones and smartwatches put up. Our quiz is pretty quick this morning, but it is no calculator, so go ahead and clear off your desk.
I can't change it.
Try to find you a pencil.
Pretty short quiz, but it does total up to 20 points, so should still double check your work before you turn it in. And once they're all in, we will move on with the handouts you picked up on your way in.
I didn't get the good comment.
Did I miss anybody else?
This one needs an operating system.
Okay.
These two I couldn't get. I tried everything.
Okay.
I gave up. I'm gonna get a bigger cart out of there for her to move her servers on.
Okay.
I just wanted you to know what I was doing.
Okay.
Alright.
Sounds good.
Mr. Townsend, is this okay for the domain, or should I write an access agreement?
Either way is fine. Whatever you're more comfortable with. If you guys are finished, please find something quiet to work on. Let people finish in peace, please. Jacob, you need to find something else to do, please. Is anybody still quizzing? It's fine if you are, I just can't tell if there's any more phones up there. Okay. then let's look ahead to your other handouts here. It's a bunch of handouts, but it's all stuff you'll be able to take care of today in class. So remember 1.9 was about inverse functions, and that's really meant to try to help you when we get to section 3.2, which is logarithmic functions. So logarithmic functions are really just inverses of exponentials, but section 3.1 we're going to talk about exponentials. So 2 of the pages you picked up today make up number 89, the 3.1 notes. The other page, the front of it is number 90 and the back of it is 91. So I'm going to go through the notes with you, just kind of as a refresher, let you know some of the stuff we're going to be looking for in this section. And then I will do worksheet 1 for you. And then I will ask you to do the same parts that I do for you on worksheet 1 on worksheet 2. So I thought that would take a little bit longer, but based on my first period class, they were able to finish all that up pretty easily today.
Mr. Johnson,
Yeah.
did you say that the back of 90 is 91?
The back of, that's correct. All right, so you need to know what it is to be an exponential function. So an exponential function is anytime you have the variable up in the exponent. So like 2 to the x, 3 to the x, those are both exponential functions because x is up in the exponent. Now, things like 2 to the x and 3 to the x and 1/2 to the x are really considered parent functions, where it is helpful if you have a general idea of what those graphs look like. But, of course, if you forgot, you could always just make a table. It's basically what your calculator does. And you could plug in some values. 2 to the 0 is 1, because anything to the 0 power is 1. We're going to use that property a lot the next couple weeks. 2 to the first would be 2. 2 squared would be 4. Of course, you could keep going to the right, but it's going to look like that. And then to go to the left, we need to remember one of our exponent properties here. 2 to the negative 1. Having an exponent of negative 1 in the numerator, you can move that to the denominator and make it have a positive exponent. So 2 to the negative 1 is the same thing as 1/2. So again, you can plug in more points to the left, but that's roughly what 2 to the x looks like. 2 is bigger than 1, so this should be an exponential growth type of equation. If we did the same thing for 3 to the x, again, I think it's beneficial to know what the graph looks like from memory. But if you didn't, you plug in a few points. 3 to the 0 is 1, because anything to the 0 power is 1. 3 to the first would be 3. 3 squared would be 9. Doesn't take too much effort to figure out what the right side of the graph looks like. And for the left side, again, you're going to need to use some exponent rules. 3 to the negative 1 is the same thing as 1/3. Oops. 3 to the negative 2 is the same thing as 1/9. What I really want you to get out of these two examples is I want you to see that these two graphs basically look the same. 2 to the x and 3 to the x. One of them rises a little bit faster to the right. One of them hugs the x-axis on the left a little bit faster. But in general, an exponential growth always kind of looks the same. So whether it was e to the x, or 5 to the x, or 10 to the x, or 2 to the x, or 3 to the x, they're all going to hit a y-intercept of 1 and have this general shape to them. Okay, if we did the same thing with an exponential decay, something like 1/2, 0 to the 1/2 would be 1, because anything to the 0 power is 1. If you raise it to the first, you would get a 1/2. If you squared it, you would get a 1/4. So exponential decay is going to hug the x-axis on the right. And then to go the other direction, 1/2 to the -1 is the same thing as 2 to the +1. You can take the reciprocal of a fraction to change the sign on its exponent. And maybe -2 would give you 1/2 to the -2, which would be 4. So we could graph more exponential decays, but again, they all basically look the same. 1/2 to the x looks like this, 1/3 to the x would basically look like this, 1/5 to the x, 1/10 to the x, they're all basically going to look like this. So when we get to worksheet 1, that's going to be one of the very first things that we do. We have to start off with the parent function, and then of course we're going to make some transformations to it. So the transformation rules are the same transformation rules we've been using all year. If you add to the parent function, it's going to make it go up that much. If you subtract from the parent function, it's going to go down that much. 6 and 7 are the two that are easy to get mixed up. Adding to x makes it go left that much, whereas subtracting from x makes it go right that much. Be careful not to mix those up. If you multiply a parent function by a negative, you're going to flip it or reflect it across the x-axis. And number 9, you probably need to put a star by, because I know you've heard of this before, but you don't use it very often. If instead of multiplying the parent function by a negative, you only multiply x by a negative, that's how you flip it over the y-axis. In fact, on the next page, I can show you how 2 to the x and 1/2 to the x are really just y-axis flips. So one of the things that we will do after we graph these and then make some transformation changes, we will ask questions like these: domain, range, y-intercept, is it increasing or decreasing, what kind of asymptotes does it have, all this kind of stuff. A few of those just typed up for you. But this guy is 2 to the x. We graphed this on the other page, so we kind of knew what that was going to look like. This guy is 1/2 to the x. Well, if I rearrange these a little bit, I could change the sign on the exponent, although I don't know why you would, but I can make it a negative x if I take the reciprocal of the fraction. So 2 to the x and 1/2 to the negative x are really just y-axis reflections. Notice if I flip this over the y-axis, it would land here, or vice versa. So anyway, just make sure you know if you put a negative just on the x, it's going to flip it over the y-axis. Okay, here are some of the properties that we will need to use since this section is on exponential functions. There's a lot of exponent properties that show up. A few of these I've already said multiple times today, but what I'm going to do is I'm going to read through and give you a quick little explanation on each of these. You need to put a star by the ones that you don't know if you're familiar with. So over here, anything to the 0 power is 1. I've already said that multiple times today. These three are all basically saying the same thing. If you have a negative exponent in the numerator, you can move it to the denominator to make it be a positive exponent. If you have a negative exponent in the denominator, you can move it to the numerator to make it be a positive exponent. If you have a negative exponent in the numerator, you can move it to the denominator to give it a positive exponent. Generally in mathematics, negative exponents are considered unsimplified. Cole, yeah, I think you need to go. So all of these are kind of the same thing, but again, please circle them so that you know to look back at those if that's not familiar to you. This is one that you guys probably use the most, but I still have to talk about this property quite a bit in calculus. If I asked you what x times x is, I think you would all know that is x squared. But the reason why it works that way is when you multiply things with the same base, you're adding the exponents. That's all this is saying. If you multiply things with the same base, you would add the exponents. Likewise, if you divide things with the same base, you subtract the exponents. So you guys probably think of it like this instead. you probably think of like x times x, a couple of those cancel out and just leave you 1. But you can also think of it as subtraction. 3 minus 2 would just leave you 1 also. You need to know a power to a power is multiplication. So if I gave an example of like x cubed squared, to square something means you multiply it by itself 2 times. And so in the end, the exponents end up getting multiplied. And then the last one, these two kind of go together. If you've got stuff in parentheses raised to a power, everything gets raised to that power. X gets raised to that power, y gets raised to that power. 2 gets raised to the third, and x gets raised to the third. If it's in parentheses, everything gets raised to that. So, not just in this section, but also with logarithms, we're doing lots of exponent properties. So again, take a second and just put a circle by the ones that you didn't remember from last year, because those are probably going to be the same ones that give you issues later on. Okay, and then finally, we do look at just a couple of applications that happen to be exponential functions. The first one is for compound interest formulas. Both of these should sound familiar from Algebra 2. We do ask that you memorize these. And as far as I know, unless something has changed in the last few years, these show up on the ACT a lot. So it's going to help you to have them memorized anyway. So these formulas work great no matter which direction you're talking about. If you're talking about an investment that you're making and you're trying to calculate how much it's going to be worth after a certain amount of time, or if you were borrowing money, how much you're going to owe after a certain amount of time. So these two formulas have quite a bit in common. So we need to be familiar with what these variables stand for. So both of these have P. P stands for principal, or the starting amount. So that could be the start of your loan or the start of your investment, just whatever you're starting with. Both of these have a T in there, which is as time in years. Both of these formulas have an R, which stands for the rate, but the rate has to be put in as a decimal. So if you want 50%, you would not put 50 in place of R, you would put 0.50. If you put 50 in place of R, you're saying 5,000%, not 50%. Always goes in as a decimal. And then the only unique thing between these two is the compounding continuously formula, the PERT formula, has a a number E. E, this is Euler's number. Euler's a mathematician. His name starts with an E. It sounds like it starts with an O, but it starts with an E. And this is just a number. So in your calculator, it's, when you need it, it's second divide. It's about 2.718. It's an irrational number just like pi is. It has a forever going decimal that does not repeat. But you only use E in the compounding continuously formula. If you compound instead a certain number of times per year, that is when you're going to put in N. N represents the number of times it is compounded per year. So if it was like annual, that would mean N was 1, because annual means once a year. If it said quarterly, N would be 4, because there's 4 quarters in a year. If it said monthly, N would be 12, because there's 12 months in a year. If it said daily, you would do N is 365. But only this formula needs N, this formula needs E. So you do need to memorize those two. So on worksheet 1, we will actually plug in some numbers into those to see how those work. The other type of application we'll talk about is about half-life. And there's not a real good example here on the notes, but it is typed up where you're welcome to read through it. You don't really need to know any chemistry or anything like that. other than half-life represents the amount of years it takes for something to decay half of what it was. So if it starts off at like 100 grams, however many years it takes to decay down to 50 grams would be its half-life. So we'll see an example of that, but you're welcome to read back through there if that seems like that might be helpful to you. And then the last thing for your notes here, you can put an X by this as far as you don't have to study it, but we want you to know where it comes from. Just like you know pi is about 3.14, but you really should know that it comes from taking the circumference of any circle and dividing it by the diameter for any circle. That's where pi comes from. The number e comes from this pattern, I guess you could say, and it just naturally occurs a lot in life. So e comes from 1 plus 1 over x all to the x as x approaches infinity. So if you put that in your calculator and you put in really big numbers for x, you would be getting close to the value of e. So again, we don't quiz you on it, but we do ask you to write it down a couple times on the worksheets, just so that you've at least heard where it comes from before. Okay, so on to worksheet 1. Again, I am going to do all of this for you, except for this question A, because we're going to talk about this next class, down about midway through the question. But you should look on the back and see that worksheet 2 is very similar. So I'm going to do worksheet 1 for you and ask you to practice worksheet 2. So make sure you're giving me your full attention here. All right, so question 1 has a bunch of parts. Wants to know basically everything there is to know about this graph, and we need to be able to do this without a calculator. So of course you could just graph this in your calculator, look at the graph, and be able to answer a lot of this. But we don't need a calculator to do this. So here's how I would suggest that you do this. You look through all of this, you need to extract the parent function, which would be 3 to the x, and we talked about what 3 to the x looks like on the notes. Just a real rough sketch. It doesn't need to be accurate. All exponential growth have a y-intercept of 1 and have that shape to the graph. Think about what the first transformation would be. If I plug a number in for x, the first thing I would do is add 1. So that's my first transformation. Adding 1 to x makes it go left 1. So take your graph here, try to make it look like it has shifted left 1. Again, just a rough sketch is going to be plenty fine. Okay, the 3 was a part of the equation, so the next transformation would be the negative out front, and multiplying the parent function by a negative is going to flip it over the x-axis. And then the last thing I need to get to their equation they actually want me to work with is this minus 1. What do you think the minus 1 is going to do? Okay, so take this graph and try to estimate it, make it look like it goes down 1. Now, with all of these, not just this one might be the most useful, but these are going to be helpful too, and this is why I think this is the best strategy here. We can answer almost all of this already. It wants to know the domain, so notice here it goes forever left and forever right. Now, to be fair, it does go slowly to the right, but it does always go to the right. Shifting it left 1 doesn't change that it goes forever left and forever right. Reflecting it over the x-axis doesn't change that it goes forever left or forever right. And shifting it down 1 doesn't change that. So it hits everything for the domain. The range is kind of hard to answer from this because this is a rough sketch. I wasn't trying to do it perfect. But I can look at this and think about the range. The range is 0 to infinity. You shift it left 1, it's still 0 to infinity. If you flip it over the x-axis, now it's negative infinity to 0. And then if you shift it down 1, it's negative infinity to negative 1. And it does not touch negative 1, so parenthesis on it too. That's where I think these steps can help you discover what this stuff is. These do have horizontal asymptotes because they approach 0 on the left. If you shift it left 1, it still approaches 0 on the left. You flip it over the x-axis, it still approaches 0. But then when you shift it down 1, now the y-intercept is at y equals -1. It kind of looks like there's a vertical asymptote, but again, this does drift to the right, so there are no vertical asymptotes. Now when we do logarithmic graphs in a couple weeks, these two will switch because they're inverses, x and y switch, so they will have vertical asymptotes and not horizontal asymptotes, whereas exponential functions are the other way. Okay, reading our graph from left to right, the graph is going down, which we refer to as decreasing. Just the bigger x gets, the smaller y gets, so decreasing over time. My first period insisted that they had never heard of concave upward and concave downward. Y'all did not hear that in Algebra 2? Huh, okay. So that's not hard, but this is a pretty, concavity is a big deal in calculus. So if it opens up, we call it concave upward. Some people say up like a cup, or concave downward would be down like a frown. So the original parent function was concave up because he opens upward. Shifting him left 1 was still concave upward. But then when we flipped him over the x-axis, now he's concave downward, concave downward. So we're just describing which direction the graph is heading. Or which direction it's opening, I guess I should say. Okay, G wants to know the order pair when x equals 1. So here's my graph. When x is 1, it's about negative something. I don't really want to guess, so how could I know for sure what y is when x is 1? Right, just do it algebraically. Y is equal to this. You don't have to go on your sketch. Just plug in 1 for x and solve for y. You have the equation to do that. Oh, yes, you're right. This would be no, wait, am I looking at the equation wrong? Oh, this would be 2. 3 squared would be 9, so this would be -9 minus 1. -10 sounds right.
Oh, so it's not, okay, I thought it was like -3. But it's -3.
Well, it is -3, but order of operations here, I have to do exponents before I do multiplication. If they wanted you to raise -3 to this power, there'd have to be parentheses to signify that.
Okay.
So you're only raising the 3 and then you're multiplying the negative. Also, if you did it that way and you thought it was 8, that doesn't, like, this is a rough sketch, but I know it's not up here at 8, so you could at least catch it that way. All right, the next question to me is the same thing, because y-intercepts have an x value of 0. So if you want to know the y value when x is 0, don't use your rough sketch. Just plug it into the equation and solve algebraically. And then you can use your sketch to make sure that answer looks realistic. If I thought it was had a y-intercept of something positive, I would be concerned that I'm getting -4 there. Okay, the next stuff, I've already thought of some of this. State the transformations needed to go from that graph from the parent function. So I already did that. I said it went left 1. I knew that was the first transformation because if I plug in a number for x, the first thing I would do is add 1 to it. The next thing that happened was the negative, which reflects over the x-axis. And then the last transformation we dealt with was the -1, which shifted it down 1. So if you approach the question the way I'm suggesting, you've already thought of that and you just need to write it down. Okay, J is one you can put an X next to because we will not quiz you on it, but I still expect you to write it down for your homework because I'm telling you what it is. Sometimes these are referred to as transcendental functions, which doesn't really mean anything to you right now. But if you look at a bunch of calculus books on the cover, they're either going to say early transcendental or late transcendental. So some calculus books likes to deal with these type of equations early in calculus, and some calculus books like to deal with these types of equations later in calculus. So that's what they're referring to, and they usually put that on the cover. So again, you don't have to study that, you don't have to memorize that, but I expect you to have it down on your paper. All right, K wants us to sketch a graph, but it wants it to be an accurate graph, not a real rough sketch. But now that I know all of this information, this is going to come together quickly. I could plot 1, -10. I could plot 0, -4. I could graph the horizontal asymptote of y equals -1. Remember, asymptotes go in as dashed lines. And my sketch gives me a general shape of the graph. I know generally what the graph's going to look like. So connect these points, make it approach that asymptote, and give it the general shape that we expect it to have. And there's a much more accurate graph. Of course, on a quiz, if you were concerned, actually I think on the quiz we might insist you do like 3 or 4 points, and that's really to kind of help you if you drew it wrong, maybe at least raise a red flag. Name the 2 points, the 2 tests that the graph has to pass to be 1-to-1. So we just talked about that. That was the vertical and horizontal line test. This passes both of those, so this is considered to be 1-to-1. Euler's number was the number E that was on the bottom of your notes. Once again, you can put an X next to this to signify that you don't have to study it for the quiz, but you still have to write it down for the homework points. The number E, that's about 2.718, comes from 1 plus 1 over x to the x power as x goes to infinity.
This survey wanted me to give this to you.
Okay. All right, thanks.
You're welcome.
Okay, part A, this is one that we will do next class when I've got more examples for you. And B and C are 2 applications that we talked about. So B, we're going to invest $2,000, so that's our starting amount, the principal. The rate is 6.5%, which as a decimal is 0.065. The time in years is 30, so T is 30. And at least the last couple years, which is probably going to be true this year, we would ask you to do this without a calculator. So the only way we can have you do that is by asking you to write out the formula with the numbers plugged in, but you wouldn't actually have a calculator to plug them in. We'll go ahead and do both for your notes. So for these 2, you would have to know continuous is the one that's referred to as PERT. So the amount that your investment would be worth $2,000, the starting amount, times the number E. Again, that's a number E, not a variable E, to the power of R as a decimal times T in years. And I believe your ACT also asks you to set it up that way. just in case you have like a calculator program that does it for you. That way they can test to see if you really know why it's set up this way. Now, to be fair, 6.5% is going to be pretty hard to come by anymore. You could probably get 5, maybe 5.5% these days. But if you could find somewhere that would give you 6.5% and you had $2,000 you could set aside for 30 years and not touch, after 30 years your $2,000 would grow to be a little bit more than $14,000. So, of course, if you didn't need that money for something else, then, you know, long term that's going to be better for you. If it's not compounded continuously, PERT is going to be compounded one of the other ways. So, same idea. You're going to have to memorize that formula. You're going to have to put the starting amount in place of principal. You're still going to plug R in as a decimal, the rate in for R. You're still going to plug in 30 for T. But what is unique about this formula is it has an N in there. N represents the number of times it's compounded per year. So since this is saying compound daily, that would be 365 times. So again, without a calculator, that's as far as we could ask you to go. But just for your overall understanding here, I will type it in. It will be very, very, very close to continuously, because compounding daily is still quite a bit. $14,054.93. So less than $3 difference, and especially over 30 years, you're not going to be worried about $3. But those are the two ways to deal with that. And again, it works the other way. It's not just about investments. It also is, if you borrow $2,000 at a 6.5% rate, which 6.5%, they're going to charge you way more than that. But if it was 6.5%, and you did a payment plan that took you 30 years to pay it back, which is pretty typical for a house, your $2,000 that they gave you up front ended up being a $14,000 bill. So you don't want to borrow money if you don't have to. But basically, you just need to know how to plug those in and memorize the formula so that you can plug those in. The last one that we need to be aware of is these chemistry type questions. And again, you don't need to really know any chemistry here. But we've got a radioactive isotope that his size in grams is this guy. There's a formula for him. And the first question is, how big is it at start? So when time is 0, what's his initial mass? Now, you should not be trying to do any shortcuts or tricks here, because you can just simply say, what is his amount? What is his mass when time is 0? Just plug in 0 for T and solve. 0 divided by 2007 would be 0. What's 1/2 to the 0 power? Because anything to the 0 power is 1. So his initial mass is 40 grams. Now, again, I know 40 is sitting there in the equation, but try not to just do it that way, because you can misremember or something. Just plug in 0 for T and solve. That's the initial. Whereas half-life, this is the one thing that you have to know about half-life, is that means how many years does it take for half of it to decay. So if he starts off with 40, his half-life will be when he equals 20. So we're trying to figure out how much time we're trying to solve for T here. So we could divide both sides by 40, and that would give me 1/2 to the first on the left, and 1/2 T over 2007 on the right. And then you should see that these two will be equal if the exponents are equal. So t divided by 2007 is going to be 1 when t is 2007. So it would take 2007 years for that made up radioactive isotope to go from 40 grams to 20 grams. Also, I don't know if you're aware of this, but anytime you guys have ever taken medicine in your lifetime, all the medicine you ever take has a half-life as well. So the very first time you took medicine, it's got a half-life, and every so often it halves, but there are still trace amounts because half never goes to 0. It just gets close to 0. So any medicine you ever take, there's still trace amounts of it still in your system for the rest of your life. So, okay, so I know a lot of that's quite a bit there, but again, hopefully some of this is familiar to you. Like I'm pretty sure you did the compound interest formulas last year, correct? Good. Okay. So the last thing I need from you guys today is flip it over, try worksheet 2, try it without a calculator, try it without looking at worksheet 1, try to do it without looking at the answers online. Just see what is familiar to you, what feels comfortable, what's not comfortable. And do all of it except for this question A, or it's not question A, it's question O. This we will save for next class when I've got more practice for you. But try the rest of it. And then when you're completely finished, check your answers. Or if you're completely stuck, check your answers. And then if you have specific questions that I can help with, then I would be happy to help out. But and y'all have just about 40 minutes, so I think that should be very manageable, even if you want to go pretty slow. And I will ask you to come back and do those questions later, the 2 that we skipped. You just don't need to do them today, but you will need to do them before you turn in the homework. I only say that because sometimes people don't ever go back and do them, even though I will ask you to. Okay. I don't. Jackson brought it in here. I don't know.
Jackson.
Christensen. I think he said it's from Mr. Reeve.
Thank you.
I don't know if it's marked or not, so you might need to remind them.
Okay.
Let me check. I don't remember seeing that. Yeah, it's not marked yet, so just make sure that they switch it to school business later.